In this video, we're going to discuss trigonometric identities and solving. So these are two separate ideas. One is trig identities, one is trig solving. So learning objectives are understand the trig identities, and we're going to use this to verify them. So this is one type of problem, is verifying trig identities. Second type of problem we're going to look at this section is solving trig equations, solving trig functions. Okay, so we need to pay attention to those words because we are dealing with two different types of problem in this section. So it's very important that you know the unit circle for this section. We'll be keep referring to the unit circle because we need to know all these values as we especially solve trig equations. Okay, so keep that in mind. Make sure to review unit circle before you watch this video. So let's discuss trigonometric identity first. An identity in general is an expression that is true for any input values. And we already seen some of these. Here's some reciprocal identities. So we know that sine theta is equivalent to 1 over cosecant theta. So this is an identity because whatever angle I put here, this angle right here, I can also put same angle here. And this equation is always true for any input. So that's why this is called an identity. This is also cosecant theta equals 1 over sine theta. This is an identity because any input I put here, pi over 2, 6 pi, or 45 degree, you'll give us same value. This is true. This expression is true for any input angles because we're trig function, that's where we're noting that input values are angles. So for any angles or any input we put, this is true for all the 6 expression. That's why these are called, trig reciprocal identities. Reciprocal because it's 1 over cosecant, 1 over secant. That's the word reciprocal comes from. Identity because it's true for any input. So let's look at some new identities that we have not discussed yet. One is called Pythagorean identity, Pythagorean trig identity. So first of all, let's quickly review what Pythagorean theorem is. Pythagorean theorem relates side lengths of a right triangle. So C is the longest side of a right triangle, hypotenuse length, and A and B are smaller length. Right? And when you square the smaller lengths individually and add them, we get the square of the longest side of the right triangle square. So this is in general in geometry Pythagorean theorem. Now we're going to relate this geometric Pythagorean theorem to sine, cosine function, trig functions. So let's look at the unit circle. On a unit circle, radius is 1, which also makes the hypotenuse of a right triangle that is formed by this angle, theta, also 1. So we have a right triangle right here. So this angle forms a right triangle. This right triangle's hypotenuse or radius is 1. So we can put 1 for C. And because vertical length of the terminal ray is sine theta, instead of A, we can put sine theta. And horizontal distance, this distance right here is cosine theta, so we put cosine theta here. This is how we get sine squared theta plus cosine squared theta equals 1. So here, well, it's kind of big, we have cosine. Well, let me actually just go to the next page. So before we go next page, let me remind you this. This sine squared theta is referring to we're scoring this entire thing. So you think as sine theta square. Think of there's parentheses here and scoring entire sine theta. Same here, we're scoring entire cosine thing of square. But the reason why we put 2 here is to not confuse squaring the angle theta. So this is a notation in trig function. When you see a exponent next to the alphabet, sine or cosine or tangent exponent, this is referring to we're applying the exponent to the entire function of the trig. So this is cosine theta. You can think this is as cosine theta times cosine theta. This is sine theta times sine theta. Okay. So Pythagorean identity, this is very important. You need to remember this one. Sine squared theta plus cosine squared theta is always 1. Whatever angle we put here, 7 pi over 6, 7 pi over 6, if you put the unit circle values, it will simplify to 1. Okay, if you put pi, it will simplify to 1. From this, we can actually deduce these two. You need to remember all these 3. So how do we get this cotangent square, cosecant square from the first one? It's because we can divide this by sine square both sides. Sine square, sine square, sine square. Sine square over sine square give us 1. Cosine square theta over sine square theta give us cotangent square. 1 over sine square gives us cosecant square. Okay, so essentially, if you remember this one, you can deduce the second one. Same for the third one. If you divide the first one by cosine square theta both sides, sine square divided by cosine square give us tangent. Cosine square divided by cosine square give us 1. 1 over cosine square is secant square theta. So make sure to remember all these, but especially the first one, since you can deduce the next two. Even and odd identities. These can be related with the graphs also. So to simply put, sine function and tangent function are odd function. So negative input angle is same as negative sine of that angle. So if I put sine of negative pi over 2, that is equal to negative sine of positive pi over 2. That's what it means to be odd function. Same idea for the tangent. Since sine and tangent are odd function, that means that corresponding reciprocal function. So reciprocal of sine is cosecant. Cosecant is also odd function. And tangent reciprocal will be one cotangent, also reciprocal. And cosine is the only even function. Cosine and secant are only even functions in terms of trig functions. So cosine of negative pi equals cosine of positive pi. Cosine of negative pi over 2 equal to cosine of positive pi over 2. Similar idea exists for secant as well. So I think for this one, simpler way to remember this is that cosine is the only even function. Cosine and secant. Once you know cosine, you can relate secant since secant is 1 over cosine. Right? These are the only even function. All others are odd. So here we're going to talk about actually doing some problems. Okay, so verifying new identities. So here's some general tips when we verify trig identities. And this is a section that you need to practice a lot because you need to build an intuition of what to do. And also, if you don't get it right at first time, don't be discouraged. It's normal for you to try more than one time to get this right. Okay? So first tip is try expressing in terms of single trig function. So in terms of sine and cosine, if possible. Right? These are general tips, and I'll look at some examples after I give you these tips. Work with only one side of the equation at a time. Okay? This makes things easier. And typically, it's best to choose a more complicated side. Okay, so maybe you don't know what I'm talking about just looking at tips. But here, let's look at an example. Here's an example, and I'm going to try to follow these tips. So the problem says verify. Okay, so technically, this is not quote-unquote solving. When we say solving in math, we usually say solve for unknown variable. Would make that equation true or inequality true? But here, Let gives us an equation. Let tells us that cosine square x minus sine square x equals 1 minus 2 sine square x. Let gave us a true equation, true expression. We just have to verify that left side is actually equal to the right side. Okay, so it is normal to take try and error. So try expressing in terms of single trig functions. Here, that it might not be relevant because everything is related in terms of sine and cosine, right? If you had tangent or cosecant, cotangent, yeah, then we can try to rewrite in terms of sine and cosine. So that's what I mean by single trig function. So here we're going to work with the left side, okay, this side, because left side seems more complicated. It's not wrong to start with the right side. It will always work if you do it right. There are several ways to verify this identity right here, this problem, but typically, it's best to choose more complicated side. And how do I define this complicated side here? Cosine square x minus sine square x. Or simply, there's one more trig expression compared to the right side. On the right side, there's only one sine square, right? Where in the left side, there's cosine square x and sine square x. So I'm choosing the left side as more quote-unquote complicated side. So how do we simplify this? Well, we know this Pythagorean trig identity of sine square theta plus cosine square theta equals 1. So we're going to use this information. So here, for this equation, sine squared theta plus cosine squared equals 1, I'm going to solve for cosine squared theta. So I'm going to isolate this one, which means I'm going to subtract sine squared theta both sides. Then I get cosine squared equals 1 minus sine squared theta. Since I subtract sine squared both sides, is 1 minus sine squared theta. So what this is telling us is that cosine squared theta is equals to 1 minus sine squared theta. How is it relevant? Well, I'm going to substitute cosine squared x as 1 minus sine squared x instead. So let me show you how that works. Again, I'm working with the left side. That's how I only wrote the left side. Now this cosine squared x, we know that cosine squared x will be equal to 1 minus sine squared x. So using that fact, I'm going to substitute like this. So I came to the next slide, 1 minus sine squared x. Well, then sine squared x, they're like terms, so we can add them with negative sign. So we have 1 minus sine squared x. And in fact, this is the right side. So we just verify that the left side is indeed equal to the right side. So we're just verifying. So showing all this work right here is part of doing this type of problem, verifying. Okay. So let's look at example 2. This is a multiple choice. This is important to really point out the notation. Which statement accurately describes the difference between cosine squared x and cosine x squared? So I actually suggest you pause and try to pick an answer on your own. When you're done, unpause and hear what I have to say about the correct answer. So pause it now. Okay, so let's go over the answer to this. The correct answer will be C. The g of x, cosine squared x, takes x as an input first. So it takes x as an input and it squares the entire output of cosine x. So this g of x or cosine squared x, this is same as cosine x multiplied by cosine x. That's what we have here. Whereas the f of x squares x first, and then input to cosine. So there's big difference between these two notations. So for example, if I plug pi over 4 for this one, it will be cosine pi over 4 multiplied by cosine pi over 4. Cosine pi over 4 square root of 2 over 2. So I'm doing square root of 2 over 2, square root of 2 multiplying each other. Whereas f of x, if I plug square root of 2 over 2, I'm squaring the number first. Square root of 2 over 2, square the number, I get 2 over 4, which is half. So here we're evaluating cosine of half radian. And cosine of half radian, it does have a value. It's just that that value is not on the unit circle. So it will be some decimal number that is not can easily be represented in a fractions we see in a unit circle. Okay, it does have a value, it's just different value. Right, so these two give us totally different values on most of these angles. Okay, so keep that in mind. The notation is very important. It doesn't matter where we put the square. This is squaring x first, squaring the angle first, and putting cosine. This is put the angle first, cosine. Whatever we get the value, we square the value. Another identity is called sum and difference identities. These are sum and difference because we can break down the angles given into two sums or two subtractions for each sine, cosine, tangent, and use that to evaluate. Okay, so this is particularly useful for the looking at the angles that are not on unit circle. For example, pi over 12 is not on unit circle, or even the half we just saw is not on the unit circle in terms of radian. So then we can break down to two angles A and B that are on unit circle to evaluate these values. Okay, so this sum and difference identities you do not need to memorize. This one will be provided. You just need to know how to use it by doing a lot of problems. So you need to practice how to use it. Okay, so don't just discount it just because you don't have to memorize. You just need to know how to use it. So let's look at an example. Find the exact value of cosine of 5 pi over 12. So now here, it doesn't say anything about sum and difference formula, right? you need to be able to identify that you have to use sum difference formula. So let me tell you how you identify. Well, you can identify by noting that, you know what? 5 power 12 is not on the unit circle. How am I supposed to find this? Well, this is where you can think of the sum and difference formula. Okay. So when the problem asks you to find the exact value of a sine, cosine, tangent of an angle, but that angle is not a unit circle, that's when you know we may need to use the sum and difference formula. Okay. So that means we need to find two angles that form, from the unit circle that we can add or subtract to obtain 5 power 12. Okay. So in this case, 5 power 12 is the same thing as pi over 6 plus pi over 4. So if you add those two numbers, common denominator, we get 2 pi over 12, 3 pi over 12, we get 5 pi over 12. And if that calculator seems too complicated, another way you can do is, this is one occasion where we can actually convert 5 pi over 12 to degrees, and then you find two angles. So, since 5 pi over 12 is the same thing as pi over 6 plus 4 pi over 6, we can write evaluating cosine 5 pi over 12 as the same thing as cosine of pi over 6 plus cosine of pi over 4. Now, pi over 6 and pi over 4, both of them are in unit circle. Okay, so we can use this cosine sum and difference formula. It tells us that cosine angle A plus B is the same thing as cosine A times cosine B minus sine A times sine B. Watch out for the signs, right? It depends on the formula, which formula we look at. And the order of A and B are not that important for addition. For subtraction, it doesn't matter, of course, but for addition, if you put pi over 4 plus pi over 6, it still gives us the same result. So now I'm going to substitute the angles. A and B are pi over 6, pi over 4 respectively. So I'll put those angles here. I should have parentheses here. So cosine pi over 6, cosine pi over 4, sine pi over 6, sine pi over 4. Each of these values right here, we can find from the unit circle. So if we evaluate from the unit circle, we get square root 3 over 2 for cosine pi over 6, square root 2 over 2 for cosine pi over 4. Multiply these, subtract sine pi over 6 half, sine pi over 4 is square root 2 over 2. Multiply, we get square root 6, square root 2 on the numerator, 4 minus 4 in the denominator. Common denominator is already formed, so we have square root 6 minus square root 2 over 4. And this is as simple as we can write it, right? We cannot subtract these two. So this is as simple as we can. This is the final answer. So we know that cosine of 5 pi over 12 equals square root 6 over minus square root 2 over 4. So this is how we use sum and difference formula when you see an angle that is not a unit circle. There are more identities. Same thing here. You do not need to memorize these. These will be provided. You just need to know how to use them. So let's just go over, let me just talk it over what these identities mean. This is called double angle identity because we have a 2 times the angle here. That's how you recognize. So we could also use this to find some values that are not in unit circle. Okay. Or we can even use the unit circle values also. So for example, sine of 90 degrees, we can divide by the 2 and put sine 45, cosine 45. So it turns out that 2 times sine 45 degree, cosine 45 degrees is same thing as sine of 90 degree. And this is true for all the angles, of course. Okay. So one thing you have to pay attention for double angle identity is that inside angle we treat as a double, whereas the right side is the half of the double angle, right? So cosine 2 theta, sine 2 tangent 2 theta. Cosine 2 theta, we have 3 options. Same as cosine, it can be used as the cosine square theta minus sine square theta, or 2 cosine square theta minus 1, or 1 minus sine square theta. This is because of the Pythagorean identity. We can replace one of these with Pythagorean identity. That's how we get 3 more. And again, you can use any of these 3 when the problem asks you to find cosine 2 theta. Tangent 2 theta is just one thing. Again, remember the left side angle is 2 theta. The right side angle is just theta. That's why this is called double angle identity. The right side, we have a half angle identity because this angle is now half of this. So sine square of, for example, 100 degrees will be same thing as 1 minus cosine of 50 degrees. Also, if this is 100, inside will be 50. So sine squared of 50 degree will be same as 1 minus cosine of 100 degree divided by 2. It's also known as power reducing because it reduces the second power to the first power trig function. So half angle because inside is the half of the angle we're dealing with. Right side is the regular angle, theta. So for identities, you just have to practice a lot to build intuition, what to do, okay? What to do on each problem when you verify or when you use identities. Now we're going to discuss solving trig equations. So these are different type of problem where we're going to solve unknown variable to make the equation true. In that case, we're especially finding the angle or angles will make the equation true. So general idea is that use algebra to isolate trig function to one side of the equation. If possible, it's not always possible. If possible, do that. And find all the solutions on the unit circle within the request domain. If domain is not provided, then you need to add period for infinite solutions. So let's look at some examples. Here it says solve 2 sine x equals 1. So since it says solve, it means we're finding all the angles will make this equation true. Because we're not verifying this is solving. So first, what we want to do is we want to isolate sine x by itself. And we can achieve that by dividing by 2 both sides. So let me go to the next line and divide by 2 both sides. So I get sine x equals half. That means I'm finding all the angles such that sine of that angle equals half. So in that case, we have an infinite number of answers, but we need to list those infinite answers. Well, from the unit circle, we know that pi over 6, sine pi over 6 is half, right? Let me use different color. Sine pi over 6 is half. But then why do we add 2 pi k? This is actually referring to coterminal angle. Any angle that's coterminal to pi over 6 will give us correct solution to this. That's why we add 2 pi k. Also, sine 5 pi over 6 is also half of a unit circle, and we add 2 pi k. So these two are the answer. These two are the correct answer right here. The precise way of saying is these two expressions are the correct answers, and these two answers represent infinite number of answers because of coterminal angleness. And k is an integer, so it can be negative 1 or 0, 1, 2, 3, 4, 5, or negative 10. So it is including adding or subtracting for rotation. Same here. So these two are the correct answers for this equation. It has infinite answers. Sometimes we will also see the restricted domain. That's what I'm talking about here, requested domain. Sometimes we will say, hey, only find the answer between 0 and 2 pi. Essentially, that means just find the unit circle values. So let's look at this example. It says solve sine x plus square root of 2 equals negative sine x for, in this case, they gave us a domain. That means 0 to 2 pi means we're only looking at the unit circle value. We should not add 2 pi k for these answers. So let's look at the equation. Sine x plus square root 2 minus sine x, negative sine x. Here we're going to isolate the trig expression to one side of the equation, everything else in the other side of the equation. So I'm going to first subtract the square root of 2, both sides. Then I get sine x equals negative sine x equals minus square root of 2. And then what I'm going to do is I'm going to add sine x both sides, this sine x. Okay. So now in this third line, we have trig expression in the one side of the equation, everything else in the other side of the equation. So we can simplify what is sine x plus sine x with two of them. So we have 2 sine x equals negative square root of 2. So then we're solving for sine x first. So we're going to divide by 2 both sides. So we get negative square root 2 over 2. And now we have a single sine expression, sine function with negative square root over 2. That means we're looking at this angle. What angles on a unit circle will give us this value? Okay. So we need to refer to the unit circle. It's 5 power 5 power over 4 and 7 power 4. In this case, only two answers because we're only looking at the unit circle. So this is an example of how solving trig equation.